And this is Lab 3, Black Hole. The purpose of this lab is to show how orbiting masses affect each other with the force of gravity. So this will be involving the velocity update formula, position update formula, the force of gravity formula, and Newton's second law. So preview is the mass of my black hole will be equal to 8.86375 e to the 33rd. And my ship's initial velocity will be equal to negative 9e7 x and 1.5 e6 y and 0 z. Okay, so for part 1, our system is the star and surroundings is the black hole. So our initial conditions is we got a lot of these constants with the star m 2.0 e30, and yeah, that's about it. Oh, and I also set count equal to 0 and total mass of the black hole equal to 0, and you'll see where this comes into play. Okay, during my code, I found the momentum initial and momentum final of the system, which is just the velocity times the mass of the star. And then I used this to find change in velocity and change in momentum. And then I found change in momentum with time using delta divided by delta, and then Fnet equals dp dt. So momentum is actually equal to Fnet. And then we use this to find parallel. So p hat is just the momentum initial divided by the magnitude of momentum initial. And then we use this to find we can find the magnitude of p, which is magnitude of p final minus the magnitude of p initial over delta. And then the dp dt of parallel is equal to the magnitude times p hat. So that's our momentum, and momentum is equal to Fnet. And then we use this, well, perpendicular is just going to be the remaining, so it's momentum minus momentum of parallel, and then Fnet is just equal to that. And then over here, this is where that count equals 0 and total mass equals 0 was earlier, because this is how you find the mass. You have to reverse F of net equals gm times m2 over r squared, and this is the equation you get when you reverse this to find mass. And then we're gonna, because each time this simulation is done, it gives you a different value, you actually have to add up each of those masses every tick, and then we're gonna count those ticks, and in the end we're gonna divide that total mass by the count. So the results is what we get this with the black hole mass equals 8.8637 e33 kilograms. And so what we can learn from this, like what does it mean, is momentum is equal to F of net for a system that's just involving gravity. Well, just always actually. And that also happens with parallel and perpendicular. Momentum is always equal to F net. Our system is ship, surroundings is black hole, and planet. And so for our initial conditions, this was our mass of the black hole from earlier. And we also have this time for how long it will be going for. And, oh, we don't know the initial ship speed. We'll see. Where we figure out the radius from the planet to the black hole. And then we use that same equation from part 1, basically, but this time it's just we're finding the force, so we just use the normal equation. And then we do that for ship to planet and ship on planet, and then we do this for ship with black hole and planet and ship. So we just do basically the same thing every time here, just with the different objects in comparison. And then we find F of net in the end by adding on the ship by adding the force on the ship plus the planet on the ship. Okay, so then we use this to update the planet velocity, the planet position, and the ship's velocity in the ship's position. Okay, results. We get this nice little orbit of the planet, and then our ship ejected from the planet, and it passed super close to the black hole and went away. And Our ship's initial speed was -9 e7 and 1.5 e6. Okay, possible sources of error are significant figures because the black hole mass could have had a lot more decimals, so we don't know exactly, and that can affect calculations. So what if we wanted to make our ship orbit? What we could do is I figured out this can be our initial speed, and it allows it to orbit, which is really cool.